So the next section in optimization is about gradient descent. If you take and pull cluster traces off of servers in a large data center, I think it's very interesting when we're talking about big data and data science. If you go and look at some of these companies who are doing that for a living, whether it's the Googles or the Twitters or the Facebooks or whatever, you really could break this down into about 4 categories of what's going on those servers. One thing is, frankly, you're moving a lot of data from one server to another. You just spend a lot of time doing that because you partition the data, you put it in one part of the cluster, another part of the cluster needs it, so it goes and just transfers it around. Spend a lot of time chewing up your network. And I like to quip that this is what other people think your data scientists do, is just move data around. And there's unfortunately a lot of truth to that. But realistically, what your data science really are doing is cleaning up data. We mentioned this before. There's kind of an 80-20 rule that you spend 80% of your time on data science teams just cleaning up the data over and over again. And there's a lot of good reasons for that, but long and short of it is if you've got a lot of unstructured data, you need to do a lot of cleanup and preparation before you can really use it. But that's also the value, being able to go out and access a lot of real-world data that's unstructured and get it into some kind of structure that's calculable. Put it into a graph. You can do a graph query. That's the real value in data science. So we spend our time doing that. And so we have machines helping us do that, and that's what a lot of your cluster is doing. The third point is something akin to stochastic gradient descent, which is perhaps what your data scientists think that they do, even though they're really actually cleaning up data most of the time. But your clusters really are spending a lot of time on gradient descent, especially stochastic gradient descent is very popular. And then fourthly, if you look at where you're spending money on your data center, probably a lot of it is for services, request response. Because really services tend to be closer to the customer. And again, for a lot of businesses, you can measure revenue loss in milliseconds in terms of latency for request response services. So, what we find when we're building really large clusters is that the people in charge who are responsible for keeping the lights running will typically allocate much more resources to services as opposed to batch jobs because they've got to hit the SLAs on the services or they lose business. And there's some great papers about this. Google did something out of Eurosys 2012, the Omega paper, where they talk about cluster scheduling. And they were reviewing their own cluster traces along with those that are published from Yahoo and I believe it was Twitter and others. And what they found was that 80% of the jobs are batch jobs, but 80% of the resources are actually allocated to services. So a little bit of advice there. That's what your data scientists should really be thinking about doing is more services, doing service-oriented architectures. When I go out and talk with really advanced teams working machine learning, they're focusing more and more on low latency and real-time use cases. And probably the best way to go about that is to think about re-architecting based on services. The point there is that after we've cleaned up our data and formulated our workflows in terms of monoids and used graph representation and parallelized with all kinds of linear algebra, at the end of the day, the heavy lifting that remains on what the cluster is doing is mostly gradient descent optimization. And so, for instance, if you look at, say, some of the great videos that Jeff Dean and others have coming out of Google about deep learning, they make the point that they have neural networks stacked up in like 10 layers deep, but the real cost there is the gradient descent that they're using to train them. And when I showed Stephen Boyd with ADMM how they had this kind of rubric for training all kinds of different types of machine learning algorithms, that uses gradient descent. As opposed to going downhill, you go uphill. It's the same thing, really. So I want to talk about this gradient descent business, and the gist of it is this. If you're familiar with, say, a topographic map, a topo map, think about standing at the top of a hill and looking at a topo map and trying to figure out what's going to be your best path down to the bottom. How do you get down to the base camp? Because if you go the wrong way, you're going to go partway down and then back up another hill. But if you read the topo map right, then you can figure out a nice route to be able to get down, hopefully not get into any kind of problems. Trying to find a short path down the hill is a good way to put it. So let's look at how this actually works. And frankly, I think this is the first part of the lecture where we get to apply some calculus. So our example company, foobartender.io, has done a little bit of analysis and found out that the cost of losing the little cocktail umbrellas, the little parasol drink umbrellas, the cost of losing those is really, it's a function of how high the drones are flying. If the drones fly at too high an altitude in the city, they catch a lot more winds, and the drink umbrellas fall off. And that's not a very good user experience. So the problem is we want to minimize an objective function, f of x, representing the cost of umbrella loss in terms of the mean flying height x for our drones. And we come up with this equation to describe the flying height, the cost of the umbrellas falling off. Turns out to be some equation. We've done some curve fitting here, I guess. And so we got x4 minus 3x cubed. And then what the last term is plus 2. OK, great. So we've got an objective function there. And we've got some polynomial, all based on this variable x. And x is supposed to represent a policy for how high are we going to fly those drones. What's the target? So we use gradient descent to basically find a derivative of this objective function. Now, frankly, for those of you who are calculus fans, you could come in here and just use differential calculus to figure out the derivative on that. We can do this on the whiteboard. But in real world, we're going to encounter much, much harder problems where solving a derivative isn't going to be quite so simple. Like when you're doing machine learning on petabytes of data and you have billions of different examples, you're not exactly going to be able to express it as something that you can take a first-order derivative off of. So gradient descent, to do this in a Python example, let me shift over to Python. OK, I've got Python here that's going to implement a gradient descent and show a simple example, again, for this objective function here, finding out where the minimum is. So I've got my gradient descent function in Python, and I'll take this and cut and paste it over. OK, so gradient descent, it's going to take a function, if you notice up there, func, and we're going to essentially do our descent down the topographic map down the hill until we find out where a minimum is for this function. And let me define what those functions are. F of x. So we've got f of x is x to the fourth minus 3x to the third plus 2. And I've solved that equation already using calculus, so that f prime is going to be 4 times x to the third minus 9 times x to the second. We can use that for some QA, just to make sure that our function is working correctly. Right. Now let me set up my parameters here. I've got a starting point. I've got a tolerance set, basically how close we're going to get to an optimal example. I've got step size, how far are we going to go on each move down the hill, how many max iterations, because I don't want this thing just to turn into an infinite loop, but I don't think it will. OK, if I paste this in, blam. So it's going to come out and it starts iterating through. You can see iteration I and what the x1 value is, basically what you're plugging in. You can see how big the error is, where the function we projected versus what you're trying to optimize, and then also the function value there. So you're correcting going down the hill. Finally, we get down here to step number 70, and we've got a very, very, very low error term, and we end up with a value of 2.25. We've minimized that function. 2.25 turns out to be 2.25 meters is the x value that will optimize the minimum of this function. And that's going to be a curve if I were to draw it out, but that'll be the minimum. That would be a policy of where we want to try to fly the drones so that the wind doesn't knock off the little umbrellas off the cocktails. And hopefully we won't run into any people who are 2.25 meters or more tall, although I do believe there's some Olympic basketball players who fit that category. Gradient descent is a deterministic algorithm. What we showed there, if I run it every time, it'll come up with the same results, if I have the same data. So effectively, it has the same cost as well. In practice, we may not have a very well-defined differential function. We'll probably need to create a classifier based on some sort of training set. It's going to be a more complex problem than what I've shown here. We're going to have, to build a learner that's based off of, more complex notions of error, et cetera. But the basic idea is, if we are training not for this function, but for a more complex thing, say we're trying to train a random forest for machine learning, for, anti-fraud, something like that. The basic idea is that we're going to use gradient descent to tune the parameters. And so we're going to optimize the learner so that it, number one, minimizes error when predictions from the learner get compared to the training set. And number two, we're going to penalize solutions that tend towards overfitting. So going back to what I showed with ADMM, you've got f of x, which is your loss function. So you're trying to minimize, how you're accounting for variance, any problems there. But then at the same time, you've got your regularization term, which means you're trying to avoid overfitting, which is to say you don't fit so closely to the training examples that you can't generalize and fit, the whole data set well. Now, with gradient descent, one of the issues is that we have to run through the entire training set on each iteration, and that can be quite expensive. If I just had a simple thing like this function here, not a big problem. But if I have petabytes of data, that's a big problem. So generally speaking, there's a faster variant of this that's called stochastic gradient descent, which basically, it also looks at that topographic map at the top of the hill. How do you find the short path down the hill? But it's going to go in hops and skips through the training data, learning from each different point that it encounters. Stochastic gradient descent is what's typically used for these algorithms. It's much more efficient, but it also introduces more knobs and dials that you have to adjust. And there's some issues where it gets sensitive to how the data is being prepared in terms of feature scaling, things like that. So, it's not quite as simple as the example that I showed in Python, but it's the flavor, the same thing, finding a way down the hill. Some great resources if you want to do a deep dive into stochastic gradient descent. Joshua Bengio at University of Montreal has a really great tutorial. Also, if you take a look inside of scikit-learn, there's some excellent examples there for Python, both of these. Okay, in terms of computational thinking, now here's a fun point. Suppose we've got these clusters, and we're running a lot of gradient descent on them, right? At the end of the day, a lot of stochastic gradient descent. So one thing that's interesting is if you take a look at, say, quantum computing, quantum algorithms, that's still a ways off, ostensibly. But one of the most interesting things about quantum computing is that you can tackle problems like really large-scale gradient descent in constant time. So if you think about this, you've got a lot of companies working with really large-scale data and machine learning, and they've optimized their workflows down to the point where the heavy lifting is all gradient descent, and that's what's running on these huge clusters, tens of thousands of servers per data center. So at the end of the day, they're paying a lot of money for those data centers to run all that gradient descent, to optimize their deep learning or whatever they're doing. But if quantum computing rolls along and it works out, that cost, that major cost basis for those clusters drops down to constant time. So I could take an arbitrarily wide number of variables and slam them through gradient descent in constant time, exponential decrease in cost. And that works out to being billions of dollars if you happen to be, a very large search engine. So you can imagine that these people are really taking a good hard look at things like quantum computing. It could be a very dramatic game changer. There's an excellent paper along these lines by Stephen Jordan called Fast Quantum Algorithm for Numeric Gradient Estimation, basically showing the point that you can get exponential increase. And there's a company called D-Wave. I know that Google bought one of these, and I think Lockheed Martin or somebody like that also. In terms of computational thinking, here's a matter of pattern recognition. If we can recognize that refactoring these really complex machine learning problems, so the heavy lifting is all basically boils down to a lot of stochastic gradient descent, we can isolate that problem and say that we've got this common resource, we've got these clusters running a lot of stochastic gradient descent. Perhaps we can apply a new technology, such as quantum algorithms, to cut that cost exponentially, make that underlying resource much, much more efficient. And I have a hunch that may be happening. As a little bit of a sidebar, it's interesting to speculate how far are we away from having practical quantum computing at scale. But as a particular data point that I find amusing, the Google Quantum AI team recently collaborated with folks at Caltech to build a Minecraft mod called QCraft. And QCraft's intention, what they've stated is that they're going to try to identify Minecraft players who are good at nonlinear thinking, who are adept at manipulating quantum physics. So they've got this Minecraft mod, and for those of you who have kiddos, you understand that 10-year-olds play Minecraft. Certainly, my girls play Minecraft a whole lot. And if you install QCraft mod, then you can go in and set up blocks to show how to do superposition, essentially how to build transporters, things like this, by building up the blocks in your VR space in Minecraft. The long and short of that is that there's probably some subset of really avid Minecraft players who are maybe 10-year-olds now, but less than a decade, they're probably going to be interns at Google AI. So we'll see if that happens, but it's an interesting data point. Hopefully so.